Hi class, today we're going to learn how to solve angled second law problems. In this problem, a person's pushing down and to the right on a 50-kilogram table with 200 newtons of force. The friction force is 60 newtons, and we want to determine the acceleration of the table. We also want to determine the normal force. I'm going to go ahead and draw a force diagram here. So gravity is going to pull down on this table, and on the legs of the table there's going to be a normal force. We can see the force on the table is pushing down and to the right, which means the object's going to accelerate to the right, which means friction's going to be to the left. We also have our applied force that's shown, but what we need to do is break that up into vertical and horizontal components. So to do that, you kind of make a right triangle around that angle theta. So here is our triangle right there. And since the force is down and to the right, we need one of those forces to be pointing down and the other one to be pointing to the right. So we need to figure out what those components are. We need to figure out how much of that 200 newtons is pushing down and how much of that 200 newtons is pushing to the right. So to do that, what you guys should know is that this is the opposite leg of the triangle and this is the adjacent. And if you remember SOHCAHTOA, let me redraw this over here. You should know that opposite goes with sine and cosine goes with adjacent. So if this is a 200 Newton force, this is going to be 200 cosine of the angle, which is 55 degrees, which is given. And this is going to be 200 sine of 55 degrees. So if we go to our calculator and make sure we're in degree mode, we can figure out how much of that force is downwards by doing 200 times the sine of 55 and 200 cosine 55 for the horizontal component. Now we want to solve for the normal force and the acceleration, and usually we can do these things in any order. So I'm going to go ahead and pick vertical forces, all right? So let's go ahead, I'm going to write vertical forces, and I'm going to look, and I'm going to highlight the vertical forces. So here is a vertical force, here is a vertical force, and here, basically this right here, is the vertical forces up and down on that table. Okay, a lot of times you can color code them. You can make all the vertical forces kind of like I did highlighted there in yellow, or you could make them, when you're drawing, you could use markers in class and make all the vertical forces a certain color to make them a little more apparent to you. So what we need to do is we need to write out a formula here. So I'm going to say upwards is positive. Now, this object is going to accelerate to the right, which means vertically our acceleration is 0, which means I can choose any direction to be positive. So I'm going to choose up to be positive. So Fn is going to be positive Fn. Gravity's the opposite way, so I'm going to subtract off gravity. And our 200 sine 55 points downwards, which means we also have to make that a negative. So I'm going to subtract off 200 sine of 55 degrees. And now you guys should know that the acceleration vertically is 0. I know the object is accelerating to the right, and we're going to find that out later. But vertically, which is totally different from horizontally, our acceleration is 0. So when I do m times a, and even though I kind of skipped a step here, I started off with F net equals m times a, my acceleration is going to be 0. So when I do this, Fn minus, the table is 50 kilograms times 9.8, that's my FG, minus 200 sine 55. So I'll go to my calculator, 200 sine 55, and I get 163.83. That's going to equal 0. And now using algebra, I'm going to do 163.83, bring that to the other side. And then I'm going to also do 50 times 9.8 and add that to the other side of the equation as well. And if I do that, I get 653.83 newtons. Now, you guys may be wondering, why isn't Fn the same as Fg? And this is a different case because of the fact that we are now pushing down into the floor. So basically, not only is not only is gravity pulling the table down onto the floor, and then the floor Fn is pushing up, but we're also pushing the floor down. So the ground has to work even harder to hold it up so that it doesn't break through the ground. So yes, now that we have angles and we are pushing things into the ground, or maybe kind of lifting them up a little bit off the ground and supporting it a little bit ourselves, the Fn is actually going to change as opposed to before where everything was pushed horizontally. The rule of thumb is that when you do these problems, if Fn is pushing into the ground or pushing downwards, the Fn is going to increase. Or if you're lifting up on the table, you're supporting some of the weight of the table. Therefore, Fn should be less than Fg. All right, so now I'm going to go ahead and do the problem horizontally. So I'll just write horizontal. And I'll start off F net equals m times a. And now I look, and I'll use a blue highlighter, and I look for the forces going left and right. And in this case, it's that force, and it is the pushing force, the horizontal component, which is actually this right up there. Now, I am going to say that the acceleration, positive acceleration, is to the right, which means the force going to the right, which is the 200 cosine 55 degrees, is going to be positive, and I'm going to subtract off the friction force, which in the problem is 60 newtons, and that's going to equal our mass of 50 kilograms times A. And then we can do the rest on our calculator. So to do that, what I would do is I would just type in 200 cosine 55. Then I would hit enter, and I'd subtract off 60. And then I need to get A by itself, so I would divide both sides by 50. So I would divide the number I just got by 50, and I get 1.09. And that's how you do these problems. Remember, if you did the horizontal first, that would be fine. Just remember, this acceleration is our horizontal acceleration. This acceleration that we just got here does not affect that acceleration in the vertical, because that is 0. It is only accelerating to the right. All right, let's go ahead and solve one more problem that is very similar to what we just did. Now we have some sort of a desk. A person's pulling up and to the right, so they're kind of moving the desk and pulling upwards with their arms, and they're pulling on a 30-kilogram desk with a force of 150 newtons. It accelerates to the right at 0.5 meters per second squared. I want to determine the friction force. So I'm going to go ahead and draw a force diagram. Again, gravity is going to pull down. There's a normal force on the legs that's going to push up. The object is being pushed up and to the right. So now I'm going to make my triangle. Here's my triangle, and I'm enclosing in theta. So it's being pulled up and to the right in this case, so that means I have to have an arrow up and an arrow to the right. And I'm going to have friction to the left. And again, let's make a little note here. My acceleration, this object's not being pulled off the ground. That'll never happen in our problems. It's accelerating to the right. Again, just like before, this angle is with respect to the horizontal, which means it's touching a line that's going, left and right. So I know that this is the opposite, so that's going to be 150 sine of theta, and theta is 15 degrees. And this down here is going to be 150, let me put the friction in. This is going to be 150 cosine theta. Just like before, we want to figure out the normal force and the friction force. Let's actually go ahead and solve for the horizontal force first. So horizontal, I'm going to do F net equals MA. Then I'm going to go ahead and highlight my horizontal forces. And here's one there. And there's my other one there. That is it. I didn't say this in the last problem, but once we split this force up, this 150 Newton force, we never use that again. We've broken that force up into the horizontal and into the vertical, and we never use that again, as weird as that seems. So now I'm going to say that positive acceleration is to the right, so I'm going to make the 150 cosine 15 degrees positive, and I'm going to subtract off the friction force, and that's going to equal m times a. So 150 cosine 15 minus the friction equals the 30 kilogram desk accelerating at half a meter per second. And if I do that correctly, let's see what I get. I get 129.89 newtons. Let me just go ahead and make sure that's correct, sorry. 30 times 1/2, and then I'll subtract off 150 cosine 15, and then divide both sides by -1, and it comes out positive, correct, 129.89. So that's my friction force. And now I'm going to do my vertical forces, and I can highlight here in green. Here's a vertical force, here's a vertical force, and don't forget, here's a vertical force. And now we're actually lifting up on this object. So we should realize that our Fn is actually going to be a little bit less than gravity because we're supporting some of the weight with the 150 sine of 15. Now the object's accelerating to the right, which means the vertical acceleration is 0, which means I can choose any direction to be positive. And again, I usually choose Fn to be positive. So I'll go Fn, and I subtract off g. But in this case, if we look right here that I highlighted in, I'll keep this in blue. If we look right here, this force is pointing upwards. It's pointing the same direction as Fn, which means that I actually have to make this a plus 150 sine of 15 degrees. And I do that because it's pointing the same direction as Fn, and I made Fn positive. And again, our acceleration is 0, so m times a is going to be 0. So when I do this, I'll go Fn minus, in this case, 30 times 9.8 plus 150 sine 15, and that's going to equal 0. And then I'm going to go to my calculator, and I'm going to do 15, excuse me, sorry, that was supposed to be a 150 right there. So 150 sine 15. I'm going to bring that to the other side. And then I'm going to add 30 times 9.8. And my Fn is going to be 255.18 newtons. And if we look, if Fn and Fg were the same, well then Fg and Fn would be 30 times 9.8, which is 294 newtons. But in this case, Fn is less than Fg because we are supporting it with this amount of weight, 150 sine 15, which is probably right around 40-ish newtons. That is about it. Thank you very much.